All right, hey again, AP Chemistry. In part two of the part one notes on energy changes and energy transfer, we're going to talk about how I would calculate these changes. So there are a couple of things that I have to look at. I have to look at the relationship between Q and M, or Q and mass. We are going to see that Q equals NH or Q equals MH is going to come up, where N is the moles or M is the mass and H is energy change associated with a phase change. We're going to see that later. So if temperature doesn't change, right? If I had the same temperature and temperature doesn't change, I got to see how much energy is associated with a certain phase. But what if I do have a phase change? What if I do have a temperature change? I will see this equation, Q equals MC delta T. So if I have any temperature change, if we mix hot and cold water, it's not surprising that the mixture will have a medium temperature. We can explain this temperature in terms of heat gained and heat lost. Measuring this heat is called calorimetry. So the equation we use is Q equals MC delta T. Q is the total heat energy in joules, M is the mass in grams, C is the specific heat capacity. This is a useful value for any substance that is changing temperature. The specific heat capacity of liquid water is 4.184 joules, grams, degrees Celsius. Notice the units are joules, grams to the minus first, degrees Celsius to the minus first, or it's the same thing as saying joules over grams degrees Celsius. A lot of the times written joules per grams degrees Celsius. What this number is saying is that it takes 4.184 joules to raise 1 gram of water by 1 degree Celsius. That's why it says per gram degree Celsius. What this is really saying is joules per 1 gram per 1 degree Celsius. And so this is known as the specific heat capacity. This is the amount of energy it takes to raise the mass and temperature of an object. And then delta T is the change in temperature. Delta T is final temperature minus initial temperature. So if I had an object and it went from 22.3 degrees Celsius to 33.3 degrees Celsius, this would be T initial. This is T final. And to get delta T, it would be final temperature minus initial temperature. And 33.3 minus 22.3 is going to be 11 degrees Celsius. That would be delta T. So if I have the mass, if I have the specific heat capacity, and I have the change in temperature, if I multiply these three together, I will get energy in Q. Okay? So I want to make sure that you know how to apply that problem. I want you to do sample problems 8 and 9. And then I am going to skip us down to keep in mind for some conversions. All right, so don't forget that mass can be represented in grams, milligrams, or kilograms, right? So there are 1,000 grams in 1 kilogram. So I could represent that as 1,000 grams over 1 kilogram, or 1 kilogram over 1,000 grams. To go from grams to kilograms, you divide by 1,000. To go from kilograms to grams, you multiply by 1,000. Or, if you're going to use dimensional analysis, if I'm going to use 1,000 grams over kilograms, that means I'm starting with kilograms. If I'm going to use kilogram over 1,000 grams, that means I'm starting with grams. Okay? And then same thing with energy. Energy can be in joules or kilojoules, same idea. 1,000 joules is 1 kilojoule. And so, same idea. 1,000 joule over 1 kilojoule over 1,000 joule. And if I want to go from joules to kilojoules, I divide by 1,000. If I want to go from kilojoules to joules, I multiply by 1,000. On the AP exam, they really don't care about how you show your work as long as you have them in the proper units. A lot of the times, they ask you to do this. They ask you to go from joules to kilojoules. And a lot of the times, they ask you to go from kilograms to grams as well. All right, so keep in mind that this is like AP questions. Can ask you to convert between kilograms and grams and joules and kilojoules. Okay, another unit that's not here that I'll throw in, we don't use it too much, but it's the calorie. 1 calorie is 4.184 joules. So if I want to convert between calories and joules, I could use this conversion factor. So to go from calories to joules, I multiply by 4.184. To go from joules to calories, I divide by 4.184. All right, and you're going to see that with the Cheeto lab. Okay? All right. Just to talk about things other than water, we don't always have to use water in temperature change calculations. This is definitely going to be on your quiz, but notice the specific heat capacities of different objects. We have large specific heat capacities and small. I'm going to make a note here, because this is on your quiz. The smaller the specific heat capacity, the easier it is to change temperature. A small heat capacity means I need less energy to change the temperature. So look at something like lead. Lead has a specific heat capacity of 0.13 joules per grams degree Celsius, but water has a specific heat capacity of 4.18 joules per grams degree Celsius. It would take 4.18 joules, right? I'm going to talk about it in terms of water, to raise 1 gram of water by 1 degree Celsius. I need 4.18 joules, but to raise 1 gram of lead by 1 degree Celsius, I need 0.13 joules. That's less energy for lead. And we could prove that, and we could do calculations, and we're going to see that lead would raise to a higher temperature. So for the same amount of energy, these would raise to a higher temperature than the ones on top. All right? And I do want to do a sample calculation. Calculate the energy required to change temperature of 2.5 kilograms of aluminum by 50 degrees Celsius. Right? Where delta T, it told you it's changing its temperature by 50 degrees Celsius. And the accepted value for aluminum, it's not in here, for specific heat is 0.9. So if I want to calculate energy associated with the temperature change, Q equals mc delta T. Setting it up, M has got to be the mass in grams. So I have 2.5 kilograms times 1,000 grams over 1 kilogram, as we saw on the previous page, 2,500 grams. Right here in the problem, it says the specific heat capacity is 0.900 joules per grams degrees Celsius. And then it told you in the problem, energy required to change the temperature by 50 degrees Celsius. Delta T is 50 degrees Celsius. All I got to do is plug and chug. So Q equals mc delta T equals 2,500 grams times 0.900 joules per grams degrees Celsius times 50. Okay? And I'm going to leave that up to you to do that calculation, but you should get a number in joules. Okay? All right. I want you to continue working on this example problem and then continue to work on sample problems 10 through 15. And then I'm going to end these video notes with calculations associated with phase change. Now, what if temperature doesn't change? Where did we say in previous notes on this heating curve are situations in which temperature does not change? Freezing, melting, condensing, boiling. Delta T is 0. There's no change in temperature. Because of that, I cannot use Q equals MC delta T. Because if delta T is 0, because there's no change in temperature, this whole thing becomes 0. But I know, just from my own knowledge, that if I freeze or melt something or condense and boil something, there is energy associated with that change. So what happens to energy at these segments when temperature does not change? Melting and freezing. Let's talk about melting. Melting is going from a solid to a liquid. H2O solid plus energy equals H2O liquid. This energy is known as delta H of fusion. I could also have freezing, which is the opposite process. I could have H2O liquid yields H2O solid plus energy. And it's the same energy, but a different sign. The energy to melt a mole of ice is called the molar heat of fusion. And this number is 6.02 kilojoules per mole. So if I have water and I add 6.02 kilojoules, I'll get water as a liquid. If I have water and I remove 6.02 kilojoules, I'll get solid. Okay? Same idea with boiling and condensing. I'll do boiling. Boiling would be going from a liquid. I need to add energy. And then I'll get a gas. And remember, if I'm adding energy, or energy is a reactant, this is endothermic. And so this energy is delta H evaporization. For condensing, I'll do the opposite. I'm going to go from H2O gas, H2O liquid plus energy. And this is the same quantity, but opposite in sign. I'm releasing energy. Don't forget that if energy is a product, it's exothermic. This energy required to vaporize water is delta H vaporization, or the energy to melt a mole, to boil a mole of water, and that number is 40.38 kilojoules per mole. So if I add 40.38 kilojoules, I should boil a mole of water. If I remove 40.38 kilojoules, I should get a liquid water. So I just want to put these numbers in perspective. For melting, delta H is equal to positive 6.02 kilojoules per mole. For freezing, delta H is negative 6.02 kilojoules per mole. For boiling, I'm sorry, you couldn't see that. For boiling, that requires energy. Delta H is equal to 40.38 positive kilojoules per mole. For condensing, this is going to be delta H is equal to negative 40.38 kilojoules per mole. Now, if I know how many moles of water I have, if I multiply it times delta H, I'll know how much energy is required. So we can use, this equation is not given in your textbook, but we could use Q equals NH. Or if you know H in grams and joules, you could do Q equals MH. Okay? So I do want to do an example calculation. All right, to calculate the heat associated with the phase change, we could use Q equals M delta H or Q equals N delta H. M is the mass in grams, or N is moles, where moles is grams divided by molar mass. Okay, and delta H is the enthalpy energy associated with a particular chemical or physical process like melting. The accepted value for the heat of fusion of water is 6.03 kilojoules per mole, or 334 joules per gram, and the accepted value for the heat of vaporization of water is 40.67. I said 40.38, but it depends on literature and textbooks. I'll just change this because I have it on the next page. 40, and it is off the top of my head too. Certain textbooks have different values because of dating, okay? All right, so you could also use dimensional analysis to calculate the heat associated with phase change. So calculate the amount of heat energy needed to boil 40 grams of water. Okay, so let me do the equation over here, and I'll do dimensional analysis over here. Now, this dimensional analysis you get from your textbook when you did your section outline for chapter 7.7 about stoichiometry and energy. So let's say I had 40 grams of H2O. I could do 1 mole and 18 grams of H2O. And that's going to give me moles. And then I could multiply by, for boiling, 40.67 kilojoules for every 1 mole of H2O. I know I got to go from grams to moles, and then I could multiply by the energy, or I could use this dimensional analysis. If all of these cancel out, I'll be left with kilojoules. Let me